Thank you very much. Good afternoon. My name is Erman Guleyruz. Thank you very much for inviting us. I'm with NCSA's industry program. Today, I'll talk about our efforts in advancing a key simulation technology for US manufacturers. So it's implicit finite element method, and it's widely used in the design of many advanced industrial products such as jet engines in aerospace industry, which is the focus of this work. At a very high level, this is a measure, analyze, and improve cycle using a finite element code, LS-DYNA, and with using very large scale real-life jet engine models. Before going into more specifics, I would like to very briefly talk about our NCSA industry program. So those are our partners. So NCSA industry program is one of the largest HPC outreach programs in the world. We have a very diverse partners from a very diverse market verticals. We help these partners with their research and development needs and their HPC needs. And actually, two of our partners here are collaborators in this project. So it's a rather unique collaboration model. It's all stakeholders on board. So this includes a large manufacturer, a software vendor, a hardware vendor. And so Rolls-Royce and Cray are our long-time partners. Let me quickly continue with a brief overview of the project. So the long-term vision is to gain the capability to design products fully in the digital realm. So this, what this means in practice is to start eliminating replacing physical tests with simulations. So this brings the pressing need for higher performing simulations, and one of the prime challenges here are large-scale system-level models with a wide spectrum of characteristic lengths. And at a high level, performance is a function of the code, the input tag, and the platform itself. Here, where our efforts are focusing on improvements on the code. So let me, and we are solving here one of the largest problems ever solved with implicit finite element method. Let me briefly describe the simulation model. It's a thermomechanical problem of a thermomechanical analysis of a jet engine. So it's a classical implicit finite element formulation with special discretizations with finite elements. So as usual, the continuum partial differential equations are turned into discrete linear systems. So here's our linear system. K is the stiffness matrix, U is the unknowns, the displacements, and this is the force vector. So we solve this rising linear system with a direct method based on the factorization of the stiffness matrix, K, here. And we use a direct method. And, as opposed to iterative methods, they're more robust and chosen for their ability to handle nonlinearities. And the general strategy is to turn this linear system into a triangular system, and then which is then very easy to solve by forward and backward substitutions. And while doing so, the sparse structure of K needs special attention. Before going into more specifics, I would like to show very quickly a high-level profile of the linear solver. So before this linear solver stage, there is input processing, which I'll talk more later. So the sparse linear solver has four main components: sparse matrix, reordering, symbolic factorization, numeric factorization and triangular solution stage. So in a nutshell, reordering is where we reorganize the input matrix to take advantage of the sparsity. Symbolic factorization, where we forecast the data structures required for the numerical factorization. And for the numerical factorization stage, where we actually factor the input matrix into lower and upper triangular matrices. So this left-hand side graph shows the scaling in time for one implicit time step. So wall clock time for symbolic factorization, the red curve is almost constant. So this is since this is currently a serial bottleneck. And the wall clock time for triangular solution, it's not shown here. It's 1 order of magnitude smaller than the rest of the phases. Right plot is the parallel efficiencies calculated based on performance on single node. Here we see that the triangular solution performs worst. I'll talk more about that. So here I would like to very quickly talk about the reordering approach. So here, the method we use is called LSG part. It's been developed by the LSTC team, and it's in a nutshell, it's a nested dissection method, and it's specifically designed to perform well at the large scales. Other well-known methods, parallel methods, reordering, field reducing methods are Parmetis and PT Scotch, and LSG part performs better than these two alternatives at high scales. And so I would like to quickly move to some performance figures here. So in practice, memory is the limiting factor in all direct methods. So if you spill out of core, your simulation can easily take 1 order of magnitude longer. So we do care about wall clock time, but memory is generally the showstopper and requires special attention. So left-hand side graph is the trace of free memory during runtime for 3 implicit time steps with the 1 million degree model. So this shows the minimum of current free memory measured every step at every minute among all nodes. So these we have collected that information with the help of Blue Water's SAS team and using their OVIS tool. These traces were exceptionally useful for us. They provided quick and high-level profiling of the code and greatly helped us to set the direction. So right-hand side plot shows the scaling of reordering in memory footprint and percent change in factor operations, the orange curve. We see very good scaling in the memory footprint per MPI rank. So, and the orange curve is a measure of the quality of ordering. So that's we see fluctuation up to 10%. That's less than ideal, and shows us there is a need for fine tuning there. Let me quickly provide a couple of highlights for the numeric factorization stage. It's a multi-frontal block low rank factorization. So it adapts well, the multi-frontal methods adapts well if the matrix is symmetric, indefinite, and pivoting occurs. It's basically at a very fundamental level, it's a sequence of dense matrix operations using the elimination tree, which has been created in the symbolic factorization stage. And the factorization consists in the bottom-up traversal of the elimination tree. And this tree, basically the practical beauty is here. This tree provides the dependencies between tasks and thus provides a natural parallelization. So here are a few performance figures for the numeric factorization and triangular solutions. So numeric factorization part is historically the most studied kernel in linear solvers. Again, these are scaling results with 100 million model. So left-hand side figure shows two performance figures. The blue is the memory footprint per MPI rank. So it flattened out at the end. So this is primarily because the load balance is designed for operations, not for storage. And as for the factorization rate, the orange curve on the left figure, it reaches around 25 teraflops with the 16,000 threads level. And right-hand side figure shows the flop counts for the last step of the solver. As you see, after making a peak, it reverses back. So this is now an open question for us, why it's after peak, why it's performing worse. So generally, triangular solutions are memory bandwidth at lower scales and MPI communication bandwidth at higher scale. So it's likely that there is a communication issue here. Here I want to very briefly talk about input processing. So we knew that the input processing was a large Amdahl fraction before we start this study. When we moved from 100 million, to 200 million model, it became a showstopper. So the standard nodes on blue waters wasn't enough for the initial domain decomposition. We first took a combo approach. We used XE and XE high mem nodes in combination, and we assigned the MPI rank 0, which handles the decomposition, to a XE high mem node. The upper plot shows the trace of a memory trace of the combo run. So it successfully handles the input processing, but hangs after the first load step. So we are still investigating what's the root cause for that. In parallel, we separated the input processing from the rest of the run. So that saved us a great deal of service units. The bottom plot is the trace of the input processing done separately on a XE high mem node. And it's the 200 million degrees of freedom model took approximately 2 hours on the XE high mem node and used around 80 GB memory. Okay, so under the title of work in progress, here are a couple of items we are working on. Some of them known to us, and some we've discovered during the study. So we are now working on the parallelization of the symbolic factorization, which is a long time serial bottleneck, and then we are working on the improvements on the constrained processing functions and also load balance and communication improvements for the factorization stage. Also, I would like to very briefly talk about quantify the long-term vision. The left-hand side figure was taken from Dr. Yoon Ho's presentation. He's with Rolls-Royce. So he describes his dream simulation having more than 1 trillion degrees of freedom. So this is, of course, with coupled physics and system level models. So we have long way to go. And I'll close with a few concluding remarks. So at the current state, we are solving problem sizes up to 200 million degrees of freedom and reaching up to 30 teraflops during factorization. We are very excited to continue this work at NCSA. Also, we recently won a Leadership Computing Challenge Award from the Department of Energy with 1 million core hours at Oak Ridge National Lab. So it will be with the same team, as this collaboration model was exceptionally successful. It was very effective in overcoming the challenges in software development at large scale. And finally, I would like to extend my special thanks to Blue Water sales team, Greg Bowers and his colleagues, for great technical support. Thank you.